Next problem 8.7. Consider the following elementary reaction. A plus B gives R and R plus B gives S. This is again series parallel reaction. We have to solve part A. 1 mole of A and 3 moles of B are rapidly mixed together. 1 mole of A and 3 moles of B. Reaction is very slow, allowing the analysis of decomposition at various times. When 2.2 moles of B remain unreacted, means 0.8 is reacted. 0.2 moles S is present in the mixture. When 2.2 moles of B are analyzed as unreacted, 0.2 moles of S present in the mixture. What should be the composition of the mixture of A, B, R, S when the amount of S present is 0.6 mole? So first 1 mole, 3 moles, and this is 2.2 moles remains unreacted. So that means 0.8 is consumed. So this delta Cb is 0.8 and delta Cb by Ca0, because Ca0 is 1 mole, so it is 0.8 moles when Cs is present in the mixture. Okay, Cs is 0.2. So from the design plot we can see here delta Cb by Ca0 0.8. So this line of slope 2, same line we are following, and this is 0.2. So from this diagonal I will move along this and will locate my point on this blue line, which is delta Cb by Ca0 is equal to 0.8. This I will move and locate the point here such that distance between this and this diagonal representing Cs by Ca0. So Cs is equal to 0.2. So here you can see I have located that point and that Cs is equal to 0.2. And here from here to here it is 0.4 and that 0.4 is Ca, and remaining is also 0.4 here, that is Cr. So Cr is 0.4, Ca is 0.4 and Cs is equal to 0.2. And this point of intersection is at K2 by K1 is equal to 0.8. Here K2 by K1 is equal to 0.8. So we have found out this K2 by K1 is equal to 0.8 for this. Okay. So analyze at various times means it is our batch reactor. From the plot, the composition when Cs is equal to 0.6. When Cs is equal to 0.6, again from this we will start from this diagonal and we'll move this, and from this diagonal to K2 by K1 is equal to 0.8. On this line we'll move this horizontally and fix a point where this Cs is 0.6. Okay, so this is matching at this intersection, this cutting here. Okay, so this is 0.9 and this is 0.3, so 0.6 means Cr is 0.3 and remaining 0.1 is Ca, and this intersection line, this you have to find out where it cuts, and that will give you further information on this. So Cs is equal to 0.6, Cr is 0.3, Ca is 0.1. Okay, here once this is fixed, Cs is equal to 0.6, then on this line of K2 by K1, this profile, this is 0.3 and that is CR, and this remaining is 0.1, that is CA. So we have noted this. CB is equal to 1.5. Okay. Now this CB, again at this point of intersection I draw a line of slope 2 and this further, so we don't have this extension, but anyway this is lying in between 1.4 and 1.6 and located roughly at the center of this. So I can say that CB value is 1.5. So CB is equal to 1.5. Now this is the reaction. A plus B gives R and R plus B gives S. To produce 0.6 moles of S. So S is produced in the second reaction only. So for this we need at least 0.6 moles of R and 0.6 moles of B in the second reaction. 0.3 moles are remaining finally here that we have seen. So 0.6 are required here and 0.3 are remaining. Means 0.9 moles of R must have been produced in first reaction. So to produce 0.9 moles of R by the first reaction, you need 0.9 moles of A and 0.9 moles of B. So 0.9 moles of A consumed, 0.1 is remaining. When you need 0.9 moles of B also. Okay. So 0.9 moles of B consumed in the first reaction, and in the second reaction 0.6 moles of B are consumed. So total 0.9 and 0.6, 1.5 moles are consumed. So you start with 3 moles. So 3 minus 0.9 minus 0.96 is 1.96, and that we have seen that it matches the value from the figure also. So when 0.6 moles is in the mixture, we have this distribution. CS is equal to 0.6, then CB is 1.5, CA is 0.1 and CR is 0.3. Part B. When 1 mole of A is added bit by bit, very slowly, constant stirring of to 1 mole of B. 1 mole of B is there and B is added, A is added slowly. Left overnight and analyze, 0.5 moles of S found. So if you remember the first plot which we have seen, where only S is formed till complete B is consumed. So R is converted to S as soon as it is formed. So no R is detected as long as B is there. So this indicates that K2 must be much greater than K1. That is what you can say about K2 by K1. C. 1 mole of A, 1 mole of B, equimolar, are thrown together and mixed in a flask. The reaction is very rapid, goes to completion before any rate measurement can be made. So you cannot measure the rate, reaction is very rapid, goes to completion. On analysis of the product, so in between you don't have a data, but products anyway you can analyze, and it is found that 0.25 moles of S is found to be present. So 0.25 moles found to be present. Equimolar, so this CB by CA0 1 goes to completion immediately. So delta CB by CA0 is 1. So on this line, this is the line of slope 2 of delta CB by CA0, which is 1. So here on this line, so you have to locate a point such that this 0.25 S should be 0.25, and you will get a unique location where along this line you can see here, if you measure this, this is not, if you measure beyond this, this is greater than zero point 0.2. So exact zero point 0.2, only one point of intersection, and here you can see it happens at this point where K2 by K1 is 0.4. So here K2 by K1 0.2, 0.3, this is 0.4, this is 0.6, this is 0.8. Okay, here. So this value, this is 2, this you have to measure. Remaining is corresponding value of CA, and this is corresponding value of CR. But it is asked only about K2 by K1. So K2 by K1 from the plot we get as 0.4. Other values CA, CR, CS also you can report. CS is 0.25. CR will be this value, whatever it is, something like zero point 4, 0.5, and between 0.6 and 0.5. Okay, and this is 2 point something, 1 to 2 point something, so that you can exactly find out from the plot, or you can find out from the calculations quantitative by the models also we have already solved.